Welcome. Today is November 23rd, 2020, and this is a NERI webinar intended to disseminate educational information and research outcomes around natural hazards engineering and the built environment. In today's webinar, we explore performance-based wind engineering with Professor Seymour Spence. This webinar is hosted by the Natural Hazards Engineering Research Infrastructures Computational Modeling and Simulation Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. For more information about NERI and the SimCenter, visit designsafe-ci.org, where you can find links to the SimCenter and the NERI Learning Center and facilities supported by the National Science Foundation. Our speaker today is Professor Spence. He is in the Department of Civil and Environmental Engineering at the University of Michigan. He earned a joint PhD from the University of Florence and Braunschweig in 2009. Professor Spence has authored over 100 publications in leading journals and conferences and was the recipient of the 2018 National Science Foundation's Career Award. The title of his presentation is Computational Frameworks for the Implementation of Performance-Based Wind Engineering. Thank you, Professor Spence, for joining us today. I invite you to begin.
Yes, so thank you, Matt. And thank you everyone for joining this webinar. So yes, as Matt mentioned, the title of today's talk is Computational Frameworks for the Implementation of Performance-Based Wind Engineering. In particular, I'm going to go through with the following slides some models and some frameworks that we've been developing here at the University of Michigan, and in particular in my research laboratory for the implementation of performance-based wind engineering. So just hang on a second here. Okay, so the motivation for this work comes from the significant damage that can occur to engineered buildings during severe wind events such as hurricanes. This is illustrated here with respect to the envelope system and hurricane winds in Florida, as well as to the structural system during these severe wind events, here illustrated in terms of some yielding and some collapses that have happened during severe wind events. So what we're going to do today is go through some of the tools that I have been developing in my research group for implementing performance-based wind engineering that are capable of mitigating these damages and losses through explicitly enabling the estimation of performance of the structural system, as well as explicitly estimating the performance of the envelope system. So we're going to look at these two aspects, and we're going to start off by looking at methods and tools for estimating the performance of the structural system. So challenges in kind of modeling and estimating the response of nonlinear or inelastic structures subject to severe winds is the need to be able to model and capture ratcheting failure in the long wind type loading, as well as the need to be able to capture failure due to potential low cycle fatigue failure. And that's going to be on a long kind of an crosswind type loading scenario where we get alternating plasticity in long duration loading. And these two kind of potential failure mechanisms are unique to wind as compared to seismic engineering, where we're more used to carrying out nonlinear analyses. So these two kind of potential failure mechanisms are kind of unique and require special attention in wind engineering. And then thirdly, we need to be able to model and capture kind of more classic instantaneous plastic collapse. So what we've been doing, or rather, before we get on to how we've been looking at doing this, some of the benefits in allowing the structural system to be nonlinear or inelastic during severe winds is the possibility of designing and kind of coming up with more economical structural systems without compromising reliability, as well as the knowledge of the ultimate response behavior of the structure, even if we don't use it necessarily in satisfying reliability targets, as well as the enabling of the use of performance-based design, which really requires knowledge of the behavior of a structural system over a full kind of range of hazard intensities. So in the tools and work and in my laboratory, what we've been doing is developing models that enable the consideration of inelasticity or nonlinearity in the structural system through allowing a state of dynamic shakedown during an extreme wind event. So what do we mean by this? So let's say we have a structural system, and that structural system is subject to a wind event, which is characterized in terms of intensity by the maximum mean hourly wind speed at the top of the building. We can then associate aerodynamic loads, so time-dependent aerodynamic loads acting on the structural system. What we want to do is, under these loads, is allow inelasticity to occur, but ensure that the state of dynamic shakedown is reached. So what this actually implies is that this state of dynamic shakedown is a performance objective. It's something we are trying to achieve to ensure safety against these failure mechanisms. So what is dynamic shakedown? Well, it is a state in which plastic deformation is produced only during a first phase of finite duration, while the whole subsequent phase is purely elastic. So if this occurs, the structure is said to shake down to a purely elastic state or to adapt to the loads. Shakedown on its own implies the finiteness of overall plastic deformation. And then using the theory of plasticity, one can demonstrate that if shakedown occurs, the structure cannot fail due to ratcheting. So that's kind of a long wind type failure mechanism for a wind excited structural system, or low cycle fatigue failure cannot occur, which is a type of a crosswind or alternating plasticity, low cycle alternating plasticity failure, or instantaneous plastic collapse. It ensures safety against these kind of failure mechanisms. So how can we go ahead and identify this state of dynamic shakedown? Well, we can use a direct approach. So in this approach, what we want to do is go ahead and consider some dynamic time-varying loads on the structural system that are periodic and infinite duration. So it's a periodic infinite duration loading. What's important to recognize here is what happens in the period is completely free, it's arbitrary. So you can consider a stationary, a non-stationary, any type of dynamic wind load history one wants to consider in that kind of period. We are just considering that load history repeated indefinitely. We then are going to go ahead and consider the material to behave in elastic, perfectly plastic fashion. That can be at the level of individual fibers, if you're looking at a fiber discretization, or it can be at the level of the section resultants, so the section resultant deformations as well as forces. And then we're going to go ahead and we're going to consider a piecewise linear representation of any yield domains we might be considering. Therefore, we're going to represent these failure domains as a series of flat surfaces. Now, this is not a limitation because we can consider as many flat surfaces as you want and get a higher resolution representation of that domain. We can get it as high resolution as we desire. So how do we go ahead then, once we have these assumptions, and estimate the state of shakedown, or whether the state of shakedown has occurred? What we need to do is go ahead and solve the following linear programming problem, where this, which is a standard linear programming problem, so it's an optimization problem, is in terms of S here. So what is S, which we're trying to maximize? S is a load multiplier. So it's a scalar that we're going to go ahead and we're going to amplify those dynamic time-dependent loads acting on the structure. So we're just going to amplify the entire loading history through this multiplier. And we're going to try and look for the maximum amount we can amplify them in terms of rho here. So what is rho? Rho is a time-independent, self-equilibrated stress state. It's the stress state that is associated with plastic distortions that occur if we are in an inelastic response regime. We're solving for the maximum load multiplier while considering the three constraints we can see beneath the optimization problem. These constraints, the second is simply the yield domain. So we've got to be inside the yield domain at each integration point of the discretization. Then the third is simply compatibility. What's interesting is the second, and this is representing the excitations within the structural system. And what we want to note here is it's actually in terms of the purely elastic steady state response in that one period of loading. Okay, so we're going to solve this one in elastic response, considering only elastic responses. What we can state then is this: if this multiplier is greater than 1, right, so we can amplify the loads above and beyond that actual value, which is when S equals 1, the structure will shake down under that loading history. So we know, even though we've got inelasticity, we're going to be safe from potential failure mechanisms. We can also observe that if we impose that self-stress state to be equal to 0, what we're imposing is that we don't have any inelastic distortions, and therefore we're actually finding the limit at which we get burst yield somewhere in the structure, which is associated with how we design structural systems for wind in current state of the practice. So if SE is greater than 1, right, what that means that under the real load history we have, we're going to have a purely elastic response state. So let's just go back a minute to this, this loading. So we said that these loads need to be infinite duration and periodic. So what does this really mean, and how do we do this? In practice, all it means is that we're going to take a wind loading history of interest of duration t, and we just consider it repeated indefinitely. Well, again, what's important here is that whatever happens in that loading period, that can be any type of load we want it to be. It can be stationary, non-stationary. It can be anything we need it to be. So, for example, what we can do is go ahead and use wind loads directly estimated from wind tunnels. So wind tunnel specific or building specific aerodynamics coming from wind tunnel tests. Or we can take that aerodynamic information and we can calibrate more sophisticated stochastic models for representing the kind of record-to-record variabilities that one would see in the aerodynamic loads. And that's what we've been doing in the models we've developed. So we've been using spectral propulsive decomposition. Therefore, using the information on how those aerodynamic loads are behaving from the wind tunnel, but then calibrating probabilistic models that allow us to capture also record-to-record variability. So this is the loading process. So once we have a representation, a model for the loads, all we need to do to be able to estimate whether the system is going to shake down or not is consider the realization of the load we want, calculate the steady state elastic response for one period of loading, and then solve that linear programming problem. At that point, we can take the multiplier, the scalar that we can multiply the dynamic loads with, and we can say that if the SE, the elastic multiplier, is greater than 1, then the structure simply remains elastic under the loads, and it's in a kind of, it satisfies current design practice, which requires that structural systems are elastic under extreme wind loads. If the elastic multiplier is less than 1, but the shakedown multiplier SP is greater than 1, the structure will shake down under that loading history. Finally, if the shakedown multiplier is less than 1, then the structure will not shake down. So these are the 3 outcomes we can get. In particular, if the structure shakes down, so that our shakedown multiplier FB is greater than 0, what we can say is that the structure under that load history is safe against failure due to ratcheting, low cycle fatigue, or instantaneous plastic collapse under that load history. So what we can then go ahead and do is consider any number of load histories you want, and we can solve one of these linear programming problems, and we get information on the distributions, the probabilistic distributions of the 2 multipliers. Now, what we can actually observe here is that that linear programming problem is extremely efficient to solve, even for very high dimensional problems. Also, in defining the constraints of the LPP problem, we only need to calculate elastic responses. And what this means is that if we have very long duration loads, for example, wind loads associated with hurricanes, we can solve this type of problem, and we can propagate uncertainties through the problem so to get estimates of probabilities of having a safe inelastic state. So non-shakedown can only be considered as one possible collapse limit. This is important. In general, collapse will involve multiple limit states. For example, we may have incapability to reach the state of shakedown, but we may also have excessive residual or peak displacements at shakedown. We may also have excessive plastic deformations at shakedown. So in general, plastic deformations are required at shakedown if general collapse scenarios are to be considered, and then estimated. Right? So one of the problems we can actually kind of highlight here is that by solving an LPP problem, which is a relatively classic way of treating a shakedown problem, we don't get any information on the plastic deformations. And that's a limit. So to overcome this, over the past 2 or 3 years, we've developed a number of new algorithms and tools to be able to solve the shakedown problem and also estimate the deformations, all the plastic deformations at shakedown. So how do we do this? We use an indirect approach. This is a path-following algorithm. Basic idea is to estimate the state of shakedown through algorithms that follow a simulated path. So the approach is based on solving a sequence of k-convex quadratic programming problems of the type shown here. While in practice, what we're doing once again is looking for increments of that self-stress state rho, here indicated as delta rho. But what we're going to do is associate with each increment of the self-stress state a increment in deformation, delta epsilon p here, so of plastic deformations. And we do this through a return mapping scheme. So what this allows us to do is that once we solve this sequence of quadratic programming problems, not only do we have knowledge of whether the structure will shake down or not, but we can calculate the plastic distortions associated with the state of shakedown. And then what we can do with this knowledge is estimate a full range of responses at shakedown, considering the inelasticity that has occurred inside the system. So we get direct estimations of residual displacements, residual stress states, plastic generalized strains at all the integration points, as well as peak responses that have contribution from the inelastic state. So we can use these to evaluate acceptance criteria associated with a whole range of limit states. So to give a summary of how this works, in practice, we need to create these finite element models in, for example, open Cs, where we model the entire structural system. We need a load model for the aerodynamic load on our system. That's generally calibrated to some wind tunnel data, so as we can capture phenomena such as vortex shedding or detached flow. We then bring these two together, and in particular, using that LPP problems together with the path-following algorithms, we can solve the shakedown problem, and we get answers to questions such as, did the structure experience inelasticity? If so, did the structure shake down? Now, with the path-following algorithms, we also end up being able to directly estimate all the inelastic quantities. So you know what the residual deformations are, peak, inelastic deformations, plastic deformations, etc. What's fundamental to observe here, for a wind event of duration of 1 hour, so let's say we take a nominal 1 hour wind event, this is around 2 or more orders of magnitude faster than using classic direct integration approaches. And if you're considering longer events, such as hurricanes that can go on for hours, these algorithms are even faster. They become multiple orders of magnitude faster than direct integration because you only need elastic response estimates. So what this means is that we can use stochastic simulation for assessing the probability of failure or the reliability of our systems, considering a whole range of uncertainties. So not only uncertainty in the loads, but uncertainties in all the properties within the system. And this allows us to go ahead and estimate system-level failure probabilities that we can then use with kind of state-of-the-art performance-based design criteria for estimating the safety of the system, or whether we meet performance objectives associated with inelasticity in the main reinforced resistance system. So let's just go through an example here. So here we're going to look at a 59-story building that is an Archetype building, which was provided to us by Magnuson and Klemenczyk engineers. This is a building which was an Archetype building located hypothetically in Seattle. It had a concrete core, it's got outriggers, steel outrigger system with mega columns. We had some kind of nominal gravity loads we were considering here. Numerical model was made in OpenSeas, had over 5,000 displacement-based beam column elements. We had like 5 integration points per element, etc. We considered a whole range of uncertainties. So here we were considering uncertainties in the structural properties, so things like the elastic modules of both the concrete and steel, damping ratios, material properties, the yield strengths of the concrete, the reinforcing in the concrete, as well as the steel members, so the steel strengths. We had load uncertainties in the dead loads, live loads, as well as the wind loads. Here we were characterizing the wind hazard using maximum mean hourly wind speed to occur at the building top, We developed a site-specific hazard curve for a lifespan 50 years. In developing this, we also took into account the uncertainties in the methodological data. We also considered uncertainties in the wind direction. To do this, we had a site-specific hazard analysis was carried out, gave us directional factors that we incorporated into the analyses, considering uncertainties in these factors as well. Record-to-record variability in the actual dynamic wind loads was captured through the spectral proportional decomposition model, where what we were doing was calibrating it to specific wind tunnel tests for that building geometry. Uncertainty generated by the use of wind tunnels was also considered in calibrating the load model. Limit states we considered, we had the component level limit state. This was a classic design limit state used in design out of today. That's first yield in any one of the members considered separately. And then we had two system level limit states. The first one looked at member first yield anywhere in the system. And then the second limit state here, LF3, the third limit state we considered in the analysis, was an inelastic limit state where what we were looking for is non-shakedown or excessive peak interstory drift anywhere in the building. That means a peak interstory drift exceeding h/100 with h the interstory height, as well as permanent set, that's residual deformations or drifts that were more than h/500. So that limit state LF3 allows inelasticity to happen in the structural system. And failure is when we get excessive peak interstory drifts, excessive permanent set, or we are not capable of reaching the state of shakedown, so we're potentially at risk of low cycle fatigue failure, ratcheting failure, or instantaneous plastic collapse. We went ahead and we calculated the probabilities of failure with respect to these limit states, considering all of these uncertainties. We did not use direct Monte Carlo here. We actually used a smart simulation algorithm to push the samples into the tail. The results are as shown here. So these are written in terms of the reliability index. So that's just transformed from the failure probability. We directly estimated failure probability and then back calculated the reliability indexes for easy comparison with target values that can be found, for example, in the 716 design code for ASCE. So we just go back to these two. These are the first yield limit states. We can see the first one, LS1, gave us a reliability index of about 3, and that's associated with first yield, considering each component separately. The second limit state is an interesting limit state, that's LS2, and it gives us the system level first yield reliability, and that was 2.8, and that's associated with yielding anywhere in the system. And that's kind of a system level limit state associated with current practice. Then LF3 here, this is our limit state based on inelasticity. You can see the reliability was about 3.3. And if we look at that a little bit more in detail, what we can see is the reliabilities associated with non-shakedown at about 3.3, while reliabilities associated with excessive deformations were actually very high. So we're looking at peak interstory drifts, reliabilities of over 4, and then with respect to permanent set, reliabilities of over 7. And what that means is that this structure, which experienced inelasticity, did not deform excessively. And this kind of illustrates the usefulness of allowing inelasticity in these structural systems. We're using the systems more by allowing inelasticity, and we're not compromising reliability as these systems are not deforming excessively. Now, if we go ahead and we kind of relate this a little bit to what we can find in literature, what we can, in particular, kind of target reliabilities coming from 716, so the ASCE 716 design code, what we can see, or load code, what we can see is that at a component level, these were the stipulated target reliabilities. Our building is right here at risk category 2 as it was met. It was designed to be risk category 2 and it achieves a reliability of 2.99. Now, if we go ahead and look at system level, and this is where performance-based wind engineering is, everything should be done and assessed at a system level. What we can actually observe here is that the reliability index at a system level of first yield, so looking at kind of classic design approaches, we can see we get a reliability which is satisfying a risk category 1 building, but not a risk category 2 building. Okay. However, if we allow inelasticity to occur safely using the criteria that we've introduced today, we can see that we can achieve a reliability of over 3.25. So we get a risk category 3 building. Okay, so we're using the structural system more, we're allowing inelasticity, we are increasing the reliability because we know that these inelastic states are safe. In particular, what's interesting to observe is that if we go back and we relate that to what type of reliability would we have to achieve using classic methods now to have this system level reliability, we would have to design to a risk category 4 building. So right now we can design a risk category 2 building and end up with classic methods and end up with a, if we look at system level performance, allowing inelasticity, kind of a risk category 3 design. So that kind of illustrates the usefulness of allowing some inelasticity and the tools that we have developed here, which allow one to quite quickly estimate where one stands in terms of these reliabilities. And this kind of brings me to this document here. This is a pre-standard that's been published in July 2019. This is the pre-standard for performance-based wind design, published by the American Society of Civil Engineers. And I've got this here because this document explicitly enables designers now to use the approaches I've just talked about. So those tools based on shakedown and allowing inelasticity at the ultimate load levels is now contemplated in this document, as are the tools that we've just outlined. So performance-based design in particular is moving towards allowing inelasticity during kind of ultimate load levels for designing the main wind force resisting system in a similar fashion to what we do with earthquake loads. Here, for more information, I've just got a list of some references that you can use just if you want to get more details in the models that I have been discussing in the previous slides, some more details in the algorithms and some more case studies, etc. So these are all publications that we've put out over the past 2 or 3 years while developing these approaches. So that brings us to an end of that kind of first part of today's presentation, which was looking at methods for the estimate of the envelope system. So what we want to do now, or of the structural system, what we want to do now is move on to the second part of today's presentation, which is going to look at performance-based wind engineering frameworks that explicitly enables the explicit estimation of the performance of the envelope system. So right now we're going to be looking at this second kind of problem here. So basically, this is a multi-hazard problem involving turbulent wind flow, wind-driven rain, as well as debris. And then existing frameworks are really focused more on low-rise buildings and are empirically based rather than model or physics-based. So they can't be easily applied to engineered systems. So basically, the models I'm going to introduce in the next few slides, we developed them with the idea of applying them to mid to high-rise buildings, and they are based on physics models and data-driven kind of models. Basic idea here is to go ahead and estimate performance for solving the probabilistic integrals shown here. So we want to be able to assess performance as the mean annual rate of exceeding a decision variable dV threshold of interest, something like repair costs associated with damage to the cladding system. We want to give, in general, a probabilistic description of the hazard and get a probabilistic description of performance through this mean annual rate of exceeding this decision variable threshold. So to do this, the first thing we need to do is give a characterization to the hazards, so in particular the wind hazard, as well as the concurrent rain event. In general here, we would also have to characterize the debris hazard, but we're not going to discuss that today. In general, the wind event through local dynamic pressures will directly excite the envelope system. It will also, through the aerodynamic loads on the structure system, excite the envelope system through interstory drifts. So both these mechanisms can cause damage to the envelope system. These damages can lead to subsequent rainwater ingress due to the concurrent rain event. So we want to be able to estimate these damages as well as the water ingress, and then take the damages, turn them in through loss and consequent analyses into envelope losses or losses associated with envelope damage, as well as an idea of the total water ingress due to the damages. That water ingress would also be used for estimating the interior losses. So with respect to the wind pressures, what we're doing here, once again, is using wind tunnel data to characterize the aerodynamics of the building. So in particular, the wind tunnel process, what we do, there should be some videos here, but unfortunately the videos are not showing up. However, once we have the wind tunnel process that's coming directly from a wind tunnel test on the building, we use spectral proportional decomposition That allows us to estimate the principal loading modes and which capture phenomena such as vortex shedding. Once we have those loading modes, we can give them a spectral representation. Using a spectral representation model, we can capture non-Gaussianity to data-driven translation models. And what that gives us is a stochastic representation of the external wind pressures. Okay, so here now, not only are we capturing the non-Gaussianity, we can capture record-to-record variability that you cannot capture if you just use that one wind tunnel realization of the pressure process, that local pressure process on the outside of the building. With respect to the rain event, we're going to represent the wind-driven rain through a time average solution. So here we're using Eulerian multiphase models. These are based on giving a representation of the mean wind field around the building using a RANS model. We then use the Eulerian multiphase model to capture the kind of turbulent dispersed rain around the building, and then estimate the catch ratio or wind-driven rain on the entire building envelope. Multiplying the catch ratio by the horizontal rainfall intensity R of H, we get the wind-driven rain on each component of that envelope system. So once we have the wind-driven rain, what we're interested in doing is estimating how the structure actually responds to the external loads in terms of drifts. To do that, we need to solve the classic dynamic equilibrium equation. For the excitation, the loads, what we do is we just integrate that non-Gaussian stochastic wind pressure model or field. Gives us the loads driving our dynamic equilibrium equation here. For the restoring forces, we can use classic finite element models. Or we can use models based on the shakedown theory that I introduced in the previous slides. And that gives us a direct estimate of the time-varying dynamic drifts in our system. Then what we need to do is actually consider internal pressures. These are also going to be dynamic. They're driven by the dynamic external pressures and any openings that may be in the envelope. Once you've got an opening, you get a dynamic internal pressure, which is governed by a nonlinear equation. You need to go ahead and solve that for each opening. So those are going to be the external openings as well as the internal openings at each floor. As you go through, what you end up doing is defining a set of nonlinear equations that need to be solved iteratively at each time step as you progress through the wind event. What's important to observe here is that one needs to update the damage status of each component on the outside of the building at each time step to ensure that the dynamic equilibrium is considering the current damage state. With respect to the damage, what we're going to do is take each one of our envelope components and consider them susceptible to a certain number of pressure-induced damage states as well as drift-induced damage states. So we will have on each component of the envelope two demands, pressure as well as interstory drifts. These are generally coupled. Then what we want to do is consider coupling between the damage states as well. So what do we mean by that? What we mean is that if, for example, a drift-induced damage state occurs, it will in general affect the capacity of that component to resist pressure, net local pressure, and vice versa. So to capture that, what we have done is we've developed models that are based on coupled fragility analysis. So in practice, we have these initial fragility functions modeling the susceptibility of the component to a certain demand. Upon the occurrence of a coupled damage state, we will degenerate those. And we do this degeneration in a probabilistic sense. For the water ingress, we said we're modeling this direct impact of the wind-driven rain through our Eulerian multiphase model, but we also need to couple that with a water runoff model because we need to realize that the water, when it hits that envelope, is going to run down. So if you get a damage, an opening, water is going to come in due to the direct wind-driven rain, but also to water runoff. So we do need to model that aspect as well. Finally, what one is interested in doing is estimating envelope losses. Now to do this, we can actually kind of use what has been developed in seismic engineering. So once we know what the damage states are at the end of our event, so we quantify exactly what the damage states are for all our envelope components, we can use consequence functions to translate those directly into losses, taking into account uncertainty in this process as well as economies of scale. And that allows us just to translate everything into estimates of losses. So that gives a kind of a brief overview of the models inside this probabilistic interval that we now need to solve to be able to get a probabilistic representation or estimation of the performance of the system. So we need, in a certain sense, to propagate uncertainty, particularly in the intensity of the event, through this integral to get the estimate of the performance. So here, what we're going to do is just briefly highlight what the intensity measures of the event are for us. The intensity measures are this vertical or horizontal rainfall intensity R of t, wind direction alpha, and then these the maximum mean hourly wind speed V of h to occur at the top of the building. These are all site specific. And implicit in here is the aerodynamics of the system, which are captured outside as the intensity measures. Okay. So it's convenient in which one's trying to solve this integral to write it just explicitly in terms of these intensity measures. We can do that just using the total probability theorem. So we end up with equation 1 shown here. And then what we can actually do is we can go ahead and kind of identify each one of these intensity measures and give them a probabilistic representation. So for example, here we have lambda or V of h. That is our non-directional intensity term. So it represents the mean annual rate of exceeding a wind speed, maximum mean hourly wind speed of interest at our site of interest. We then have this term here. This is a complementary cumulative distribution function of wind direction given wind speed. It's a conditional distribution function. And this one here is going to model the directional characteristics of the site-specific hazard. What's important here is to recognize how to estimate this, we do need knowledge of the joint probability density function between the wind speed and the direction. And then finally, we have this term here, which is the CCDF of concurrent rain intensity given wind direction and speed. Now, this would be a complex term to estimate. There's two conditional two parameters here associated with the wind event. However, data suggests that actually this dependency is very weak. So in estimating in practical scenarios, one can take it as independent of wind direction and wind speed, making it quite straightforward to estimate. Now, to evaluate this integral, in theory, one could do it analytically. However, analytical approaches break down if one kind of considers how high dimensional these integrals are, because here it looks like it's a fourfold integral, but actually it has a much higher dimension than that, because we're taking into account the stochastic nature of the loads. So these have dimensions in the order of thousands. So analytical approaches are not really possible. Direct Monte Carlo approaches can definitely be applied. However, they have a huge computational burden because we're really interested in small failure rates. So in general, what one has to do is use some type of smart simulation, stochastic simulation scheme. So in the citation, which I've got here at the bottom of the slide, you can find some that we've developed over the past couple of years specifically for solving this integral here with a limited number of samples. So let's go ahead and just look at a case study here. This is again an archetype building to illustrate this performance-based framework. So here it's a 45-story building located in Miami, Florida. The duration has a nominal length of 1 hour. We're considering a steel structure. It's got some X bracing on the kind of smaller, shorter faces. The cladding system, what we're interested in, is composed of 3,600 dual-pane laminated window panels. Now, each one of those panels, we're going to consider them to be susceptible to 2 drift-induced damage states associated with glass cracking and then glass falling out. Okay, and the demand here is interstory drift. And then we're going to consider each component also susceptible to a net dynamic pressure induced damage state associated with glass blowout. These damage states, we're going to consider them coupled. So the occurrence, for example, of the first drift-induced damage state will result in a loss of capacity for resisting net pressure of around 10%. The occurrence of that second drift-induced damage state will result in a loss of capacity against net pressure of about 90%. In implementing this framework, we do consider these as uncertain, but it's very hard to exactly quantify these types of dependencies, so these are treated as uncertain when we do the simulations. The hurricane hazard, so we need to describe the 3 intensity measures, so the horizontal rainfall intensity, wind speed, and directions. With respect to the rain, what we did actually, we extracted data and fitted the CCDF directly from the US Weather Bureau. So that's giving maximum horizontal rainfall intensities in Miami during hurricanes. For the wind event, what we did, we used a database from the National Institute of Standards and Technology. They have databases of wind speeds and directions associated with various mileposts from the coast of the United States, and we chose Miami. That allowed us to directly quantify the site-specific hazard curve, so that's a mean annual rate of seeing a maximum mean hourly wind speed at the top of the building, as well as the joint probability density function to get the directional term, and we did that through the use of coupler functions. Aerodynamics, we characterize the local net pressure through a database from the Tokyo Polytechnic University. We calibrated the stochastic model I kind of mentioned earlier. To do that, we used a kernel-Pareto mixture model for capturing the non-Gaussianity. That was a translation model using the kernel-Pareto mixture model. And we used 10 spectral modes to capture the energy. So what we have here is just some kind of typical kind of or representative illustrations for some pressure coefficients over the building height. So here, if we look at the three plots that are on the left, what we're looking at are the marginal PDFs, probability density functions of the pressure coefficients. So in blue, we have kind of the Gaussian PDFs of the local pressures. And then in black, we have the actual target data. So you can see these are highly non-Gaussian. So local pressures are generally highly non-Gaussian, so it must be captured if you're looking to calibrate the model, the stochastic model. In red, we have our proposed models that we are using based on that kernel-Pareto mixture. You can see that we very easily capture the non-Gaussianity in the pressures. On the right, the three plots on the right are looking at the power spectral densities of the pressure coefficients. So in black, we have the targets, that's coming from the wind tunnel data. And in red, we have what we, the spectral densities from the simulated signals. So what we can see is as we move towards the higher frequencies, we are still capable of capturing the energy with 10 spectral modes. So that's just illustrating how 10 spectral modes was sufficient to capture the dynamics of local dynamic pressures in this case. And this is just a quick kind of illustration, just a visual illustration of the difference between the wind tunnel time histories that we have and one simulated kind of representation of the pressures. So if you looked at the black, so on the right, we have the wind tunnel, on the left, the green, that's the simulated. You can see that just visually looking at, so we are capturing the kind of stochastic nature of the pressures, local pressures. With respect to the wind-driven rain, a question that could come up would be, well, if you're doing a stochastic simulation, don't you need to run the wind-driven rain, Eulerian multiphase model for each realization of wind speed and wind direction? So in general, the answer to that would be yes. But to get around that, what we use is interpolation. So what we do is we run some predefined wind directions and some predefined wind speeds, and then we can interpolate for any other wind direction. So here we just have one or two of the wind speeds and directions that we, or wind directions that we considered in setting up that interpolation scheme with the wind-driven rain. So here we get to the results, kind of output you get from these types of frameworks. So here we're looking at envelope damage. So what are these? These are probabilistic damage maps. So what we're looking at is a mean annual rate of any one of those envelope components on the building facade, having as a final damage state one of the three damage states we defined, right? So the first damage state was drift induced, it was glass cracking. The second was drift induced, it was glass fallout. And the third was pressure induced, it was window component blowout. So at the very top, the first panel down on the right is showing us what's going on at the component level with respect to that first drift induced damage state, so the mean annual rates. So you can see we do have a certain probability of these the components having drift-induced damage. The second, kind of the middle map, shows us the mean annual rate associated with the second drift-induced damage state for all the components. And we can see that's a little lower than the first damage state, as it is less likely to occur. And then at the bottom, the lowest panel at the bottom, what we have is the mean annual rate of having as a final damage state one is the window blowout. And we can see that is what's actually governing the performance. That's the highest rates. We can see these rates are low because these are buildings that are designed to perform well. So the actual probability of losing windows in severe wind events is low. Hence, we need to simulate into the tail to be able to generate these types of maps. So this here, what we're looking at is for each component within the system. So what we can now do is go ahead and aggregate these results and end up with system level maps. So here what we have for plots. So here what we're looking at is the mean annual rate of exceeding a certain number of components in a given damage state at the end of the event. So the blue curve there, that is mean annual rate of exceeding a certain number of components in a pressure-induced damage state at the end of the event, while the black and the red are looking at the two drift-induced damage states. So what's interesting to observe here is that while the pressure-induced damage state is the governing one, the drift-induced damage states, the black and red curves, do exist and not negligible. They do exist. You should also observe here that these results do consider the coupling between the damage states. Finally, we can go ahead, once we have these damage states, we can then know, if we know what the damage states are at the very end of the event, we can translate those using consequence functions into system level estimates of losses and consequences. So here what we can see on the top right is the mean annual rate of exceeding a repair cost associated with the damages to the cladding components. Okay, so we can see that as we move up for low failure rates, we do begin to see quite a significant amount of damage occurring to this cladding system. Well, the bottom panel is looking more at the consequence of that damage. That is the mean annual rate of exceeding a certain amount of water ingressing into the building due to the damage to the cladding event. And if we look at that, we can see for small failure rates, 10 to the power of -5, etc., there is a significant amount of water will get into these buildings, causing significant internal damage. These kind of measures here, they were estimated using stochastic simulations. We can deaggregate them any way we want, like we do with classic performance-based design. So, for example, looking at the water ingress, we can deaggregate that to kind of packets of 3 floors, and we end up with the following plot, which gives us the mean annual rate of having a certain amount of water ingressing every 3 floors. So it gives us an idea of where is the water most likely to enter. We can deaggregate any way we want. This is just an illustration, so we could deaggregate those to each floor, we could deaggregate them to a building face, and we can deaggregate it right down to a building or component level. So it's very general, allows a lot of flexibility in defining the performance metrics. So again, here, just for more information on these approaches, what I've done here is I've just added in at the bottom there some more citations. These are associated with those performance models that we've developed for implementing performance-based wind engineering and the envelope system. So those are where you can find more information, more detailed information on those models and how we apply them to the case studies. So this kind of brings us to our concluding slides. So in general, with respect to the performance of the structural systems, so the main wind force resisting system, performance-based design and tools, what we did, we ended up looking at some efficient computational frameworks for characterizing the inelastic response based on dynamic shakedown theory. So contrary to direct integration approaches, these models can estimate the inelastic response for a single windstorm in a matter of seconds. And this is even true for very long duration windstorms. So we're looking at estimating inelastic responses, so actually a safe inelastic state for these systems within a matter of seconds for windstorms that can go on for hours. So this is a very efficient and practical approach to allowing inelasticity. Then by combining with stochastic simulation methods, we looked at how we can actually end up defining computational tools that allow us to give us the probability of failure for the system, so system inelasticity. We looked at being able to directly estimate that using combining these tools with stochastic simulation. And we kind of illustrated that on an archetype structure. In the last part of the presentation, we looked at computational models for performance assessment of the building envelope of wind-sided structures. So this framework kind of integrates wind tunneling form stochastic loads, CFD, wind-driven rain models, and coupled fragility-based damage models for estimating the damage at the end of the wind event. And then we saw how we can then integrate that with loss and consequences to get system-level estimates of losses in terms of metrics that are familiar to those who work in performance-based design in general. So again, we illustrated this on a case study where we kind of saw the importance of considering both pressure and induced damage states, as well as the amount of water that actually can get in to these buildings once these the envelope systems get damage. So with that, come to an end. So I would like to thank everyone for their attention, everyone who is online, and I'll be happy to take any questions. Before moving on, I would like to acknowledge the funding for this work. This was coming from the National Science Foundation, through the grants shown here, as well as the Magnus and Clementic Associates Foundation. So with that, I'd like to thank you all. I'd like to open the floor to any questions.
Great, thank you, Professor Spence, for this informative presentation. It was really great. And at this time, we'll transition to some questions from the audience. I think the first one is the optimization related to the shakedown computationally intensive?
No, that's the really, really good question. So whenever one tries to kind of set a problem involving optimization, if the optimization is time consuming, then this approach wouldn't really be of any practical interest. So the trick here is that what we can do for the shakedown is turn it into a linear programming problem. So a linear programming problem can literally be solved for very large systems. So when I say large systems, I mean three-dimensional representations of building structures, like the archetype we saw up in Seattle. And we can solve that programming problem in a matter of hundreds of a second for each sample. So the actual programming problem is easily solved. So the optimization problems. And that's true also for the quadratic programming problem. That's a little slower, so we're not talking about solving that at the same speed, but we can break the optimization up to each integration point within the discretization, solve them in parallel, and that means that we can still solve these very efficiently.
Great. And the next question is the impact of where the failure starts, for example, in the base plate or connections within the roof, are those considered? And I think the failure initiations depend on the wind direction, leading to several possibilities. So can you touch on those?
So absolutely. So we have a completely unbiased representation of where failure can start. So when we do the discretization of the system, we will discretize every single element we believe to be susceptible to damage. So it has 5 integration points, 5 per element, and each one will have a yield domain associated with possible failure. And we don't give any precedence to which one starts. It just is dictated by the loads on the system. With respect to which wind direction, that's an excellent question. So there is no way of knowing which storms to choose to do an analysis. So again, that's where one of the kind of start points of this research was. So we don't have a way of easily identifying windstorms where we would like to go ahead and say, well, if it's safe for this windstorm, it's safe for everything, because that seems very arbitrary. So the basic idea was to develop methods that can identify collapse or safety against collapse. So I would say these models identify safety against inelastic collapse mechanisms that are fast enough that we can have a statistically representative set of storms that we can then go ahead and analyze. That's considering all the wind directions. So for example, the case study I showed had 12,000 windstorms of 1 hour duration considered. So those were probabilistically meaningful storms. So they had different wind directions with probabilities for wind direction associated with what we saw at the site, as well as the wind speeds, as well as record-to-record variability in the stochastic dynamics loads. So we had all of these ingredients put together, and we just considered them using direct stochastic simulation. So unbiased representation of where the failure systems can start and what storm was going to cause it. So then at the end, the reliabilities we get are just reliabilities associated with potential failure under a complete representation of the windstorm at that site of interest.
Okay. Another question is the applicability of dynamic shakedown to other structures. For example, electrical transmission towers. Is it appropriate for other structures or just buildings?
Absolutely appropriate for other structures. Our funding happened to focus on buildings. So a lot of the work we did focus on buildings. There's absolutely no reason not to apply that to electrical systems. So we're talking probably about the towers. Absolutely, yes, you can go ahead and apply them. You could apply them to also, for instance, thinking of wind farms as well. There's no reason not to apply this approach to those structures as well.
Okay, I think this will be our last question on shakedown. Can you explain how dynamic shakedown behavior was established as a performance objective? In other words, what factual information established this type of behavior that prevents occurrence of the limit states outlined? Maybe the question
Yeah.
there is.
So the theory of dynamic shakedown is actually something which dates back to plasticity theory. So this is actually in the 70s, 80s, as well as the 90s. So basic mechanics. So the state of dynamic shakedown as a phase in which any kind of mechanical system will pass before reaching failure exists, mathematically proven to exist. So in practice, you have a structure, it needs to start yielding. Once it starts yielding, you first need to always pass through a phase of dynamic shakedown where you have inelasticity, but if you allow the loads to continue, that inelasticity just dissipates. If you increase the loads enough, you get outside of that stage, and then you will not shake down anymore, and you get to collapse. So it's actually a mathematical state that exists due to the theory of plasticity. That state can vanish. So it's not like it always exists. It can vanish in certain structures. If you calculated it, you would find that if you don't design it properly, you end up with a vanishing state of dynamic shakedown. So you go from kind of first yield to potential failure without transitioning into a state of dynamic shakedown. And that's really related to how redundant your system is. The more redundant it is, the larger the state of dynamic shakedown will be. So that is kind of demonstrated from classic plasticity theory. So what we were doing was, okay, can we take this and can we generalize it into tools, create tools that can actually estimate that state under stochastic dynamic loads? And computationally, can we develop tools based on finite elements to be able to implement that theory? So that's what our focus was. So the existence of the state, we can find it's something coming from the theory of plasticity.
Okay. If we can talk now maybe a little bit more about the second part of the presentation. And in this case, the question is, you've showed some fragility curves for estimating the damage state of the cladding.
Yep.
Are those fragility curves derived from FEMA? By that, I presume they mean P58?
P58. Yes. The short answer to that is yes. And I would like to underline that obviously that is not strictly correct, right? Because we're looking at wind actions. So one thing, if you look at the P58 carefully, one thing it does say is that the fragility functions that were derived, if you do use them for other types of actions, which are similar, because we're looking at, for example, you were looking at drifts, dynamic drifts coming from wind excitation or from seismic excitation, they still are dynamic drifts. And they are dominated by the dynamics of the building. So they have a similar kind of frequency content as well. So the overall possibility of using those fragilities is to a certain extent acceptable. One thing, if you look at the P58, it says that if you use them for different loads, you need to increase the dispersions. So one thing we did is that we increased the dispersions. So we took those limit states and then we maximized the dispersions to what was kind of indicated in the P58 if you use fragility functions for different types of actions, or you have little knowledge of exactly how the actions are going to be on the component which you're describing its susceptibility through that fragility function. Then the second, that we did have pressure fragility functions. Those were directly estimated for wind. So the window blowout fragility functions are for estimated explicitly for wind. But the drift ones, no, they came from the P58.
Okay. The next question from the attendee is, for the water runoff over the building envelope, do you assume all of the runoff above the opening will enter the building?
So all the runoff at the level of the above the opening will enter, yes. At the moment we do, that's a conservative estimate, but we do at the moment consider all that water runoff entering in. But that's a good question. Should it be all of that? It's difficult to ascertain. To actually model what happens once you have an opening and you know pretty much how the water runoff is occurring above it, to model exactly what happens at the opening is complex. So kind of to err on the side of conservatism, we said that all that water would enter, but that's not necessarily true. That's a good, excellent question.
And follow up from that same attendee is, while calculating the losses, does the water ingress impact the nearby room in the building, or is it averaged over the whole floor area?
So that's a really good question. So again, what we did here today was not consider losses induced by the water ingress. So what we were doing with these frameworks is we're looking specifically at the cladding, and we're estimating what its damage state is and how much water is coming in at each damaged location. At that point, we stopped doing the analyses. Hence, the interior loss models were kind of grayed out, because today we didn't discuss any models for taking that information, which is local in nature because we know where it's entering, and translating that into interior damage, because that is another aspect which would need to be treated.
And we're about out of time, but I would like to add just one more question from one of the attendees. They're wondering about the simulated dynamic wind loading for the case study you published in 2020. Which software did you use, and where could somebody obtain that loading data set and other be able to replicate with what you presented there?
So the data we calibrated it to is the Tokyo Polytechnic University pressure database that is publicly available. You just need to look up Tokyo Polytechnic University and then put in pressure database, maybe pressure database high-rise buildings, and then you'll directly go to that link. You can find all the pressure data there. That's the data. The stochastic model, we didn't use a software. That's all written by ourselves in MATLAB. So the model, that model is not at present publicly available.
Okay, well, I think that concludes the question and answer session. Thank you very much to the attendees for your presence here. To Professor Spence, thank you for the presentation and taking time to answer these questions. It was a really great and informative presentation. For additional webinars, I'd like you to check the SimCenter's website at simcenter.designsafe-ci.org. If you have other questions for Professor Spence, I think his contact information was included in the bio. And I want to thank you both, to the attendees and to Professor Spence, for the webinar today. Thank you.
Thank you. Thank you to everyone for attending.